Okay, we're starting. We're going to do like another curve sketching example. Make sure we understand how to do that, all the things that are involved. And then we're going to move on to optimization, which you guys hopefully brought the handouts for. Last time we drew a graph that we all know how to graph already, the 1 over x squared, but we sort of went overboard with the details, and we're going to do the same thing, but we're going to do it with a polynomial this time. So we're still in curve sketching. I actually want to do example C from the handout, which is x to the 4th minus 4x. We're going to go through all the steps for this guy and sketch the graph at the end. And they're all the same, so I think. So, step 1, what is it that we look for?
Domain.
Domain. Right, because sometimes afterwards when we're finding a bunch of points or finding critical points and stuff like that, we want to know whether they are actually on the graph, and so it's good to know the domain ahead of time. So we're going to check the domain, and for here it is. Yeah,
Just all your numbers.
yeah. Everything works because it's a polynomial. That one was easy. Next thing we look for? Intercepts. So we're going to look at x and y intercepts. And especially curve sketching, these are one of the problems that are going to be very tedious, or it's one of the longer kinds of problems. So you really want to know what you should do first, second, third, and really it should be dialed in. So we're going to find the x-intercepts. How do you find those?
So B0.
Set y equals 0, solve for x. How do you solve that?
B0.
Huh?
No.
Factor. So we can factor out an x cubed left of x minus 4, and so we get x equals 0 or x equals 4. So there are 2 x-intercepts. So make sure whatever picture you draw at the end, it has 2 x-intercepts. Y-intercepts is when you plug in x equals 0 and solve for y, so you just get y equals 0. Third step. What's the third step?
On the asymptote.
Find any asymptotes. Okay, what are the asymptotes for?
No.
There are none. Why are there none? It's a polynomial. Polynomials do not have asymptotes. It's like I totally guessed. Like polynomials are like the counterexample for everything. Right? So remember, you have a vertical asymptote if there is some number on the number line where your graph like, shoots up. Polynomials don't do that. Polynomials gradually increase off to infinity. Also, we know there's a horizontal asymptote if, as you take the limit as you approach infinity, there's some horizontal line that you used to level off at. And again, polynomials don't do that. Right? The polynomials, we know that if the highest power is odd, the polynomial would just go off to infinity. There's no horizontal asymptote. If the coefficient is positive. And right, so things like x to the n where n is even, the ends of a polynomial will look like that. If you have x to the n where n is odd, the right side will go up and the left side will go down. If you make these negatives, of course it flips, but that's how polynomials behave. They don't hover anywhere or approach, and they don't randomly shoot off to infinity at some finite x value. Polynomials don't have that behavior, right? So if you set up those limit equations, they will not give you what you want. So they're none. Right? Polynomials are defined everywhere, and they don't have asymptotes, and so you can just write none because it's a polynomial. So move on to step 4. Now things start getting interesting. Step 4 is where we find increasing intervals of increase, decreasing, any possible maximums and minimums. And what do we use to find that? Right, but what do we need to find the critical points? Right. The first derivative, right? First, okay? So we're going to find the derivative of this guy, which is
4x.
4x.
now find critical points. Remember that's where f prime equals 0 or undefined. This, again, it's a polynomial, so that's not going to happen. So it's always defined, so we're only worried about this equation. So we never worry about the undefined case in the polynomial. And so we have 4x cubed minus 12x squared equals 0. Hope you all remember how to solve that now. That's factor out the common 4x squared. And we would be left with x minus 3. So then this means that x equals 0 is a critical point, as well as x equals 3 is a critical point. Now, how do I figure out what kind of points those are? Well, now we have to test them. And test them on like a number line. Because so this helps us to both identify what the critical points are and at the same time determine where the function is increasing or decreasing. Because we're going to be testing it in the first derivative, and the sign of the first derivative is going to tell us about it. So we're going to plot these two here, 0, 3. Remember how we test them? You pick a random number inside of each interval. So let me just pick minus 1, pick 1. And pick 4. You can pick any numbers you want, so just pick one that's easy to deal with. Don't pick like a million, even though a million would technically work. Just pick 4. Right? Pick the smallest numbers that you can calculate. And so, yeah, if I plug in -1 into the derivative, which I plug it into the factored form, it's more convenient in general, because I don't care about the value, I care about the sign. You'll also notice in the factored form that this first part here is squared, right? Which means it's always going to be positive. It's never going to change the sign. So really the guy that's controlling the sign is x minus 3. So I can literally only focus on the x minus 3 to determine the sign. So if I plug in -1 into x here, that's negative. So over here, we're negative. If I plug in 1 into x minus 3, that's still negative. So right here, it's negative. Plug in 4 into x minus 3, that's positive. So here it's positive. So what does negative mean?
It's decreasing.
Decreasing. So I know the graph is going down, right? So that's decreasing. Somewhere here, it's decreasing. And here is positive, so it's increasing. So, any maximums or minimums? 3. 3 is going to be a minimum because 3 is in the domain of the function, and we're decreasing when on the left, increasing on the right. So that ends up being a minimum. Any maximums? No maximums, right? Because to be a maximum, you have to do this and then that, right? So there are no maximums. Any inflections?
Don't we have to take a second derivative?
Exactly. So if you try to answer at this point, you're totally off. The first derivative does not tell us about inflections. Okay? To talk about it, it's not a thing we can talk about looking at this chart, right? First derivative tells us about increase and decrease in maximums and minimums. We cannot talk about inflection by looking at the first derivative. So it was a trick question. Right? So that's not something we can know here. But so far we know that it has a minimum and we know where it's decreasing and increasing. So we can just write that down. especially if this is a part of the question where I ask you to tell me where it's increasing or decreasing, you want to write it down. So we can talk about increasing, where are we decreasing, where do we have maximums, where do we have minimums. So we're increasing and you just state the intervals, so from negative infinity to 0, union from 0 to 3, and we're, that was decreasing. And we're increasing from 3 to 3. Maximum, there are none. Minimum at x equals 3. If I want to find the point, the coordinate where this minimum occurs, what do I need to do? Yeah?
Plug it into the original equation.
The original. So you need to remember the original is what tells you about the points on the graph. So if I ever want to find a coordinate for something, I would plug into the original. So here my y would be 3 to the 4th minus 4 times 3. And what's that? So you're allowed to use your calculator. You could also, like, technically you can factor. I know students don't normally think about this, but the laws of algebra, they work when you're dealing with just numbers. So basically what we could do here is we could factor out a common 3. We'd be left over with 3 minus 4. So that's 3 cubed times minus 1, so it's minus times 1. But anyway, so 3 comma minus 27 is the minimum point. It's a local minimum. Polynomials, the polynomial won't have an absolute max or min if you're looking on the entire interval. So that's where we're increasing, decreasing, and where we have maximums and minimums. That ends the 4th step. The 5th step is to find what? Concavity and inflection points. Concavity and inflection points come from the second derivative. So we're going to examine the critical points of the second derivative. And the second derivative is, I don't remember what. So it was x to the 4th times 4x cubed. And the first derivative was 4x cubed minus 12x squared. And so the second derivative is going to be 12x squared minus 24x. And so again, we're going to find the critical points of this guy. So set this guy equals 0 or undefined. It's a polynomial, it's never undefined. Here there's a common 12x I could factor out, which is x minus 2. So that becomes x equals 0, x equals 2. And so now I'm going to test that. This is called a concavity test. In the second derivative. Pick random numbers inside of each of these intervals and plug into the second derivative. I take a minus 1, plug in here, that's negative, times negative, so that's positive. Plug in a positive 1 here, that's positive, but that would be negative, it's negative. Take 3, plug in here, that would be a positive, times a positive, so it's positive. And what does positive mean here? concave up. So it's concave up like a cup, so you should be shaped like a smiley face. So when it's concave up over here, this is obviously negative is the opposite, concave down like a frown. And here it's concave up like a cup. So that's how our concavity ends up being. Any inflection points?
From 0 to...
Right, both of these are inflection points. An inflection point is where you switch concavity. If I look at 0, on the left I'm concave up, but on the right I'm concave down, so I switch concavity. That's an inflection because 0 is in the domain. Here as well, if I'm at 2, if I'm on the left I'm concave down, if I'm on the right I'm concave up, and 2 is in the domain of the function. So that's an inflection. So I have 2 inflection points. So let's take an account of what we have so far. We know where we're concave up, concave down, and our inflections. So we're concave up here and here. And we're concave down in the middle. We have inflections at x equals 0 and x equals 3, but x equals 2. So if I want to find the coordinates, I plug into the original function, goes y equals 0. If I want to find the y value here, I keep erasing the original. So I believe that. So I'm going to plug that in. 2 to the 4th minus 4 times 2 cubed. So that is 2 cubed times 2 minus 4. That is minus 2 to the 4th. So we know that 0, 0 and 2, minus 16 are inflection points. And with that, we have all the information to sketch the graph now. Let's do it over here. And now you're going to summarize all the previous steps on this picture. So, what do we know? Domain is everything, so that's okay. What was our intercepts? X-intercepts?
0 and 4.
0 and 4. So we plot those 0, 4. The y-intercept was just 0. There will only be one y-intercept because it's a function. And let's see, what else did we? The next step was asymptotes. There were no asymptotes, so we don't have to worry about that. The next one was increasing, decreasing, max and min. Okay, so tell me about that. What's the increasing profile? Where are we increasing?
3, 4.
Huh?
From 3 to the right.
From 3 onwards? So from here to infinity?
Yeah.
Okay. So let's draw a little slash there. Here we're increasing. And we were decreasing.
Negative infinity to 0.
So from here all the way up to 0, we're decreasing. And we're also decreasing here. We had a minimum, right? Where was the minimum?
3.
It was at 3, comma.
27.
So let's just put a random point down here. Let's call that 3, comma, minus 27. And there was no maximum, right?
No.
So we know that this is a minimum here. Let's label that. And so we move on to the next step, concavity, which is still here. we're concave up to 0. We're also concave up from 2, that 2, onwards, we're concave up, and we're concave down in between 0 and 2. And we had 2 inflections, so this guy's an inflection, and we had another one at 2. Let's just put it here. Make that minus 60. And that was all the information. So now we have all the information, we can start to sketch this graph. So you go region by region, how we broke it up. So we're over here. We know we're decreasing concave up. So we're moving down as we're going from left to right, and we're shaped like a smiley face while doing it. Obviously we have to hit 0, so if we're decreasing, we have to be above 0. And so we're coming from up here. And that's this region of the graph here. So I'm decreasing, but I'm curved like this. All my tangent lines are below the graph, it's concave up. So now I move into the next region, which is here. Here I'm concave down, and I'm still decreasing. Okay? So I'm still falling, but now how I'm curved while I'm falling is going to change. I need to be concave down, so I need to shape like a frown. And so this switches like that. So I bend like this, then I bend like that, because that was an inflection. So I'm concave up here. And try to make it a little, emphasize it a little bit more. So I'm concave up, switch the concave down, because that's an inflection. Still decreasing all the way. And I'm still decreasing, but this is another inflection. And I switch the concave up. So bending this way, bending that way, now bending this way again. I have 2 inflection points. And I decrease all the way until I hit the minimum. And so now I have to start increasing. And I'm increasing concave up, so I'm shaped like a smiley face while increasing. So that's what the graph is. And at this point, I mean, you have to be careful when you're graphing, because I will have to grade you for how you're curved. So if you're curving this way and coming down, or you just make it like a straight line, that's not technically correct. I mean, you don't have to be super specific because you're not drawing on a graph paper, so I randomly pick these numbers, but the shape of the graph is going to be very important. I will be grading you on the fact that your concavity is correct, and if your graph looks fat or skinny, doesn't matter so much, but you need to have the concavity right, you need to be passing through the right points, you need to be able to identify inflections versus minimums and all that stuff. All that's going to be important. So that's the end. Any questions? So again, curve sketching, another thing where there's like a standard procedure. This was the final step, step 6. Of course, the steps will look different because you'll be given a different function all the time, but you go through the same kind of process all the time. And in that sense, we'll start the next topic, which is going to be very similar in that sense. There's a very standard procedure that we use to do it. That's going to be optimization. So I gave you the handouts last time, hopefully you have it. If not, you can pull it up from the website. Now, optimization is a huge deal. It's a very one of the main applications of calculus. There are other methods of optimization other than using calculus, but sometimes calculus is the way to go. To optimize something, and we're looking at optimization that I gave you last time. So to optimize something, in a nutshell, means to make it as good as possible. You want to achieve the optimum situation. It turns out that sometimes, though, that can be phrased in such a way that it describes something being as large as possible or as small as possible, right? So you might, in the case of a business, for example, when you talk about the optimum situation, there are measures that you want. I want as much profit as I can get. I want as small as cost as I can get, right? There are things where you can say, I want this to be big, I want that to be small, right? So that would be the ideal situation. So a lot of times optimizing really means making something as big as possible or as small as possible, or in other words, finding maximums and minimums, right? So if you can figure out a profit function, I want to know where the max profit occurs, or if I figure out a cost function, where does the minimum cost occur? So we need to be able to look at maximums and minimums, and as we've seen, calculus allows us to identify points like that. I can figure out where maximums and minimums occur. Another issue, though, is that there are always constraints in doing this, right? So you can be like, I want the maximum amount of profit possible, but you have a finite amount of employees. You can only produce so much products. You can only sell so much products, right? Your sales team is only so good. There are always limits, right? You can't make an infinite amount of money because you don't have an infinite amount of resources and an infinitely efficient distribution system, for example. So there's always going to be something that's kind of constraining the best possible situation. And so a good optimization system has to take that into account. Sure, we want to make things as good as they can possibly be, but there are always limits on how good things can be. There's always a constraint, some sort of restriction that you have. You don't have an infinite amount of resources and energy to get something done. So that brings us to optimization. We want to be as good as we can be within certain constraints. And so that's what we're going to do. We're going to try to figure out functions that describe a situation that we care about. We're going to want to maximize or minimize something in the presence of some constraint. And that leads us to optimization. There, again, like related rates and like curve sketching, like some other things in this class, this will be a word problem, but there's a standard sequence of steps that you go through to solve these word problems. Right? And so we're going to do some examples later, but I just want to sort of go through this. Step one, as always with word problems, read very carefully, because one, you need to know that it's an optimization problem as opposed to a related rates or something else, right? Two, you're going to want to draw a diagram to describe the situation if you can think it would help you out. A lot of times there's going to be some geometrical component to it. Three, and this is different from related rates, we're going to need to set up two equations at this point, right? One equation is going to describe the restriction that we have. There's going to be something that's constraining us. The second equation is going to describe the thing that we want to maximize or minimize or optimize, make as best as possible. So that's called the objective equation. And the constraint equation is obviously the one that talks about the constraints you have. Four, it turns out your objective equation is the one you're going to want to focus on. That's the one that you care about. But usually we'll have several variables in it, and we don't know how to deal with several variables in Calc 1. That's a Calc 3 kind of thing. So what we do is we want to get the objective equation in one variable, and you always do that by step 4. Use the constraint equation, solve for one of the variables, and plug that expression into the objective equation. Okay? Now that does two things. It gets your objective equation in one variable, which is good, but it also means that your restriction is built in to the formula that you're working with. So now you know once you find a solution to that, it takes into account the restriction. Okay? And 5 is where the calculus comes in. Here we're going to want to actually optimize things. We're going to find the absolute maximum or minimum of this new function that we've created to figure out the best possible scenario. And A comment on this is that the endpoints are rarely ever a solution, at least in Calc 1. So usually it's going to be a local max or min that's going to help you out, but you do want to find, you do want to think in the absolute sense. And 6 is to answer the problem. So you're going to be asked for something very specific. They ask you for dimensions, make sure you give them dimensions. If they ask you for a cost, make sure you give them the cost. Make sure you answer what is required of you. That's kind of it in a nutshell. I think the best way to illustrate the steps is to actually do an example. And the first example I think is very nice to do. It's easy enough so you won't get bogged down by the actual example, the facts of the example. And at the same time it illustrates the sections very well, I think. It's also similar to the Jevon's llama problem that you saw in the review when I was trying to build a pen in my backyard to hold all the llamas. So it's a similar idea to that, but we're going to apply calculus to it and get through that. So let's actually do optimization, which I forgot what section we said, but I think it's 4.6. And we're going to do example 1 from the handout. We might be able to get through a second example, but I'll do maybe a couple more on Friday. So, step 1, read. Farmer has 100 feet of fencing and he wishes to make a rectangular enclosure. If he wants the enclosure to encompass the maximum possible area so that he can plant the maximum number of crops, what should the dimensions of the enclosure be? So here's the setup. A guy has 100 feet of fencing, wants to build a fence, but he wants to maximize the area. So this is an optimization problem. It talks about some situation where you want to make something as big as possible. Okay? And we need to figure out what the dimensions should be. Okay? So, first thing reading this, can anyone sort of tell me what is the constraint here? What is the restriction? Is there a restriction on this farmer?
You only have 100 feet that way.
The amount of fencing. He doesn't have an infinite amount of fence. If you want the maximum area, build an infinitely long fence and fence around the whole world. No, he only has 100 feet, right? There's a restriction. Whatever he has to do, he has to do with 100 feet. And then you start to realize he kind of has many options, right? You can do a 25 by 25. You can also do something like a 10 and a 10 and then a 40 and a 40, right? Or you can do something like, a 30 and a 30 and a 20 and a 20, right? There are many options for this fence. You want to find the best one. You want to find the option that has the maximum area. But the constraint is you don't have all the fencing that you feel like you should have. You only have 100 feet to get it done. So that's where the constraint comes in. So the first thing we did is we read the problem, we understand. We want to maximize something under some constraint. This is an optimization problem. 2, let's figure out a diagram to describe the situation. He wants to build a rectangular enclosure, so a rectangle seems to be the best diagram. And we're asked for the dimensions, which means we don't know the length or the width. So I'll just label those, call it X and Y. There's my diagram. Now in the third step, we're going to set up 2 equations. There's a constraint and the objective. So this describes your restriction. This describes the thing that it is your objective to maximize your minimums. So we already said the constraint is the amount of fencing he has. In terms of the scenario that I just set up, what is that describing? According to this picture of the situation. Yeah?
2x plus 2y equals 100.
Exactly. The length around this object, the perimeter is the constraint. So I drew a figure and I realized the perimeter is the constraint. The perimeter has to be 100, which means that 2x plus 2y has to be 100. Or I can say x plus y equals 50. All right, so this is a constraint that you have to obey. The length plus the width has to add up to 50. That's a restriction that you have. That, by definition, is your constraint equation. Now you go to the objective equation. So this is what you want to maximize or minimize. And what is that here? What is you want to maximize or minimize? Area. So the area equation is what you want to maximize. So the area equation is obviously going to be the equation I want to do here. So the area, based on this diagram I just drew, is going to be what? X times y, length times width. That is your constraint equation. And this is actually the equation I care about. The area is what I want to make as big as possible. A couple issues though. One, it has an x and a y in it. So I'm not sure exactly how to find the maximum of a function that has two variables in it. That brings us to step 4. This is to plug the constraint into the objective. Now what that involves is you just solving for one of the variables and plugging it into there. And in general you can solve for any variable you like. So just by random choice I'm going to solve for the y. Because there seems to be everything seems pretty symmetric here. There seems to be no benefit in solving for one as opposed to the other. So I solve for the y. What that means is I'm going to plug that in to the area equation. So this y I'm going to replace with this. Now at this point, we do get that this is an inverted parabola. Technically I know this and I can figure out the maximum using the vertex, but in general, you won't get a parabola here, so let's pretend we're not going to use this method, we're going to use calculus. Because there's no vertex formula for a general curve. So this happens to be a quadratic. You notice that? You can use the vertex, totally valid, but let's actually use the calculus to figure it out. This is why I could ask the llama problem earlier, because technically you didn't need calculus for a problem like this. But you will need for the others. Okay, so now 5 is we want to maximize A. How do I maximize this function? How do I find the maximum? Find the derivative. It means that the maximum is going to be like a critical point. So that means where A prime equals 0 or undefined. So I'm going to find the derivative. It's going to be 50 minus 2x equals 0 or undefined. 50 minus 2x is a polynomial, never undefined. So I have one solution here, which x is 25. Also, technically I should be finding the absolute max, so I will consider the endpoints. So the largest I could attribute to x, which is one side of the fence, is 100. Right? But of course, we reject that. Because if I devote all 100 to x, I have nothing to devote to y. So that would create an area equals 0, which is obviously not the best fence you can build. Similarly, x equals 0 is the smallest possible. So I'm looking at the endpoints here. But again, I would reject this possibility because that would again give area of 0. So that if I devote nothing, that's obviously not the maximum area. So it turns out that this guy should be our maximum. So what I can do is here is I can test. And in practice, if there's only one possible answer, that's going to be the answer. But in general, you could get several x values, so you have to know which one you should pick. And so probably testing would be the way to go. So if I test in the derivative at 25, I know it has a minimum of 0, maximum of 100. So I'll pick a random number here, like a 1. Pick a random number here, like a 26. Plug into the derivative. If I plug in 1 here, that's a positive number. Plug in 26 here, that's a negative number. So it turns out that this is the maximum. Like I said, these, in practice, they won't really be an issue, but at least I want to see that you're considered. The endpoints will rarely ever give you the best situation because they usually is something so extreme that in a physical context it's not going to make sense to consider it. But so far, now we can get to 6 because we've done step 5. So this is just to answer the question. So what were we asked for? We were asked for the dimension. Which means, if you just write down x equals 25 as your answer, you didn't answer the question. Okay? I asked you for the dimension, which means you need to tell me what is the length and the width. So based on our diagram, we know that the length, that's equal to x, which is 25 in this feet. And we also know that the width, that was equal to y, which was 50 minus x, so that's also 25 feet. So we need a 25 by 25. And that is an optimization problem. So there are scenarios when you want to make something as good as it can possibly be in some sense. That can be phrased in terms of maximizing or minimizing something. And this process allows you to do that in the presence of some constraint. So at the end of the day, you should be solving someone's problem by telling them what to do and how to set up a certain situation. So we'll stop there. I'll do a couple more examples on optimization next time. All the homeworks up to curve sketching are due on Friday. But I'll do more examples here. So we'll stop there. And what homework is due today?
4.2.
And 4.2 is due today. So 4.3 to 4.5 is due on Friday.
No, I said it's on. Actually, no.